So now let's discuss one important theorem regarding this eigenvalue and eigenvector, the Cayley-Hamilton theorem, which is quite a simple statement. So we'll not go for the proving theorem here because it you can refer any standard textbook. Okay, so we'll just use we'll just see what is Cayley-Hamilton theorem and what is the significance of it. So what it says is it's every square matrix satisfies its own characteristic equation. So this is one important statement. So what it means is, so say if I have A as a square matrix and its characteristic equation is basically determinant of A minus lambda I equal 0. So this is basically, say if it is a 3 by 3 matrix, then this will be a cubic equation. So let's say lambda cube A lambda cube plus B lambda square plus C lambda plus D is equal to 0. Okay, so basically first will be any of 1 only, because when you multiply it comes out like that. So now this equation, what this theorem says is that when this is a characteristic equation, it says that the square matrix also satisfies this characteristic. So what it means is, in the place of lambda you can substitute the matrix itself. So this will be lambda square I, because the order has to be, it is A square plus C. In the place of lambda you are keeping A, that's it. So this will be the last, it will be identity matrix. So it's basically a matrix equation. So that's the basic idea. Okay, so this is what it means. So it's quite a simple theorem, but this relation that putting putting A in place of lambda, or basically the matrix satisfying its own characteristic, that is an important fact, because it will be helpful in evaluating your A inverse. We'll see how A inverse can be evaluated very easily. Okay, so application of this Cayley-Hamilton theorem is evaluating higher powers of matrix, and also inverse calculation will be very easy. Inverse calculation is easy. Okay, so now let's take a small problem. So let's now take a problem. If matrix A is given as 1 2 2 2 1 2 and 2 2 1, find the value of A square minus 4A minus 5I. Okay, you need to find out the value of it. So let's see whether what does this mean. So first let's find out the characteristic equation. So characteristic equation will be det of A minus lambda I is equal to 0. So det of A minus lambda I, and that means 1 minus lambda 2 2 2 1 minus lambda 2 2 2 1 minus lambda of that is equal to 0. So this we have to just use the determinant. Okay, and once you calculate this, the value comes out to be 1 minus lambda. So just evaluating determinant, minus 4 and then minus 2, this minus 2, because of this when you're writing minus 2 into this cross multiply. So I know how, I think everybody knows here how to calculate determinant, because that was the starting sections we have seen. And then plus 2 Okay, 2 into 1 minus lambda minus 4 is equal to 0. So when you simplify this value comes out to be let me just simplify further. 1 minus lambda whole cube minus 4 1 minus lambda minus 4 1 minus lambda minus 8 plus 4 1 minus lambda minus 8. So this 4 1 minus lambda and plus 4 1 minus lambda will get cancelled, and so now when you simplify this, so this is equal to 0. So when you simplify this comes out to be minus lambda cube plus 9 lambda plus 3 lambda square plus 5 square. So this you have to just manually simplify it, and I'm just writing out the final expression. Okay, so this, okay, this is the expression. Now this actually you need to factorize this, and this comes out actually minus 1. If you now any one root you need to now search. So when you try to factorize this comes out to in the form minus lambda square plus 4 lambda plus 5 into 1 plus lambda is equal to 0. So this is somewhat tricky. How do you, now you can guess the value first of all, like here whether lambda what is the root. Okay, you can guess it, and now use Cayley-Hamilton theorem. So it says that in the place of lambda you can put a. So let's put a, and we get minus a square plus, so this is 0, so it means that minus lambda square plus 4 lambda plus 5 is equal to 0. Okay, the other root cannot be 0, so well this can't be 0, I mean this, because lambda plus 1 is equal to 0. So if you substitute a there also, so you will get either minus a square plus 4a plus 5i is equal to 0, or a or 1 plus a is equal to 0, or that means I plus a is equal to 0, but a can't be I mean because a is already given. Okay, so this a can't be minus I. Okay, so we are left only with this, and that is what is asked, a minus 4 square, a square minus 4a minus 5 is equal to 0. So the answer for this is 0. Okay, so now this expression, had it been, if you don't know this eigenvalue thing, eigenvalue concept, what you would have done, you would have just multiplied a square, you would have just computed a square multiplied with minus 4a, and then basically computed the value by normal multiplication, matrix multiplication. By knowing this Cayley-Hamilton theorem, you can just evaluate this, but only thing is once you should know the characteristic equation, and then a basically satisfies characteristic equation. Okay, so that is one new thing, Cayley-Hamilton. Continuing with this problem, actually you can, I mean though it is not asked, you can just evaluate. This was the problem we got, right? And you can, as I said, you can evaluate A inverse quite easily. So how? Well, I can write I as A inverse in the above equation, and that is by the definition of A inverse, right? A inverse is basically A into A inverse is I. So I can write this expression as 5A inverse is equal to null matrix. Now this entire thing I can express in this form, A into A minus 4I minus 5A inverse is equal to null matrix. Well, something has to be 0. Null matrix, you can understand in this way, this gives, actually this has to be 0, but probably the best way to understand this would be take this matrix, okay, a square minus, so these I mean this is also one proof, but let's begin like this. A square minus 4a minus 5i is equal to null matrix. That 5i I can take other side, And now if I 5i, now if I multiply by A inverse throughout, so I can get A square A inverse minus 4A inverse is equal to 5i A inverse, right? And now A square A inverse can be written as A inverse, I can write, minus 4A inverse is I is equal to 5i A inverse is A inverse. So I can write, now this A inverse is I and A into I is I. So A minus 4i is equal to 5A inverse, and therefore A inverse from the right hand side would be 4, sorry, so using this right hand side, I can write A inverse is equal to 1 by 5 A minus 4i. Okay, A minus 4i. So this we got from this also, I mean setting this equal to null matrix because A can't be 0. So this is one proof, or the other proof is this. Other proof is this. So the basic point is, as I told you in the applications of this Cayley-Hamilton theorem, you can easily evaluate A inverse. You can express A inverse in the powers of A or A square. But here it happens that A inverse is just purely, you have to just compute A, subtract with 4i, and divide by 1 by 5. So A inverse of matrix can be easily evaluated once you know the characteristic equation, because once you know the characteristic equation, you know that the square matrix also satisfies that characteristic equation. That is what the Cayley-Hamilton theorem says, and then you can easily evaluate inverse of A, because inverse of A, otherwise in the normal routine procedure you would find out adjoint and then find out the determinant and then divide the adjoint A with the determinant, so it takes some time. But once you know this Cayley-Hamilton theorem, you can easily evaluate. So once you know Cayley-Hamilton theorem, you can easily evaluate A inverse. Okay, now let's see some more problems on eigenvalues and eigenvectors, basically dealing with the properties of eigenvalues and eigenvectors. So let's now see some problems based on the properties, whatever we have studied. Okay, so for matrix A, which is given as 1, 2, minus 3, 0, 3, 2, 0, 0, minus 2, find eigen vectors in fact eigenvalues of 3a cube plus 5a square minus 6a plus 2i. So we have to basically evaluate the eigenvalues of this, so based on the properties. So now first let's evaluate the eigenvalues of the given matrix A. So for that I need to write the characteristic equation, which is det of A minus lambda I is equal to 0. So for that I need to basically evaluate the det, replacing the diagonal terms with the diagonal term minus the lambda. Okay, now this I have to evaluate. This comes out to be basically 1 minus lambda. So determinant is just, because it's basically a triangular matrix, so determinant will be just product of the diagonal terms. Okay, and so the values of lambda come out to be 1, 3 and minus 2. Okay, so the eigenvalues of A are 1, 3, minus 2. Now, so eigenvalues of A cube will be what? A cube will be basically 3 times of it. So 1 into 3 cube minus 2 cube. So implies 1 comma 27 comma minus 2 whole cube. Remember, this is minus 2 whole cube, so 1 comma 28. Okay, and now eigenvalues of a square will be basically the square of implies 1 comma 9 comma 4. Okay, and eigenvalues of I, you know, eigenvalues of I is nothing but its diagonal terms, which are 1 comma 1 comma 1. Okay, now so let's find out the eigen first. I mean, complete it. Let's consider the complete expression. 3a cube plus 5a square minus 6a plus 2i. So now we have studied that in the properties of eigenvalue, that if we have a plus ki, then the eigenvalues are basically the eigenvalues of the sum of, I mean, if you have two matrices A and B, the eigenvalues will be sum of the eigenvalues of sum A plus B will be individual sum of the eigenvalues of A and B. Okay, so I can just find out the eigenvalues of A cube, multiply it with 3, and so now for this entire thing the eigenvalues will be 3. Let's first calculate the first eigenvalue. First eigenvalue of this will be 3 times a cube. Eigenvalue first is 1, then plus 5 a square, first eigenvalue is a first eigenvalue is 1, plus 2 1. So this value comes out to be 4. 3 plus 5 8, minus 6 14, plus 3 plus 5 8, minus 6 comes out to be 2. 2 plus 2 4. So that is first eigenvalue. Now the second eigenvalue, so you have to basically take another 3 a cube, this is 27, plus 5 a square is 9, minus 6 a square is a square we have already written. A eigenvalue is 3 plus 2 into 1. So this value comes out to be 110. 3 into 27 81, plus 45 minus 18 plus 2, that comes out to be 110. Now the third eigenvalue will be basically 3 minus 8, 3, okay, it's minus 2 whole cube, so this will be minus 8. Actually we have not written minus here. Okay, minus 8 plus 5 into 4 minus 6 into minus 2 here because of a this thing. Okay, and then plus 2. So this value, if we evaluate, it comes out to be 10. So now you can clearly see the eigenvalues of this expression. If you want to evaluate it individually, it takes a lot of effort. You have to just compute a cube, a square, then a 2, and then you have to just sum all that and then write down the characteristic equation of this entire thing. So by knowing just the properties, you can individually evaluate the eigenvalues of a cube, a square, and then you can just add, I mean, as per the given equation, you can just compute the eigenvalues. So the eigenvalues comes out to be 4, 1 1 0 and 10. So these are the 3 eigenvalues of the given expression. So knowing the properties is also important, because some cubic or fourth power or the second power and some given expression of matrix, you can just evaluate the any matrix which is just any matrix which you got by multiple or scalar or any operations on matrix A. So any combination of matrix A you can just evaluate once you know the eigenvalues of matrix A. So that was the point. Once you know the and another important point you need to remember here is that the identity matrix, okay, which is given as 1 0 0 0 1 0 0 0 1. So this has eigenvalues 1 comma 1 comma 1, and any eigenvector any vector is an eigenvector. So this is clearly visible, right? These two are important facts, but this is clearly visible because if you just let's say how, let's try to derive the eigenvalues of this. So when I write down the characteristic equation, it comes out something like this, and now the det of this is 1 minus lambda whole cube is equal to 0. So implies lambda has all equal roots. So these are the eigenvalues for the identity matrix, because this is a somewhat special matrix. And any vector, now you can see that when you multiply any vector with identity, any vector with identity, you will get the same vector back, right? And this being the case of, that's why here what you got, lambda here is 1. So I need not actually prove it, I mean I need not take determinant also. Directly if you put this matrix in this form, as per definition, you can say that any vector when you multiply with any vector, when you multiply with the eigen, any vector you multiply with I, you will get back the same vector, and this is basically 1 here. Okay, so these two are important facts to remember. These two are important facts.